So right now you're filling out the seating chart. If you are on Zoom, make sure you put your name down here, that's where you are.
So I emailed them. About me.
I think I just need to get. I just need to give them.
Oh, so
I was just so
do you have this? Do they?
they didn't tell me because I think I need to give this to you. I don't know how it works. I guess if they have to buy, that's fine.
Okay, I will call and I will double check.
Also, for my exams, is it okay if I take it at that time?
Yeah, because you have another class right after. Yeah. So just when you schedule it.
I'll let you know.
No problem.
Okay, so make sure that you are entering in your, wherever your seat is for today on the Excel spreadsheet. And if you're on Zoom, I think we had a few people on Zoom. Somebody on, Juliana, go ahead and put your name down here. Okay, y'all, please remember with your masks, make sure they are covering both your nose and your mouth at all times. Nose and mouth. So today we are not going to do eye clicker, and I'm going to tell you why in just a minute. I give everybody the normal time to get in here. So I guess I could start with some jokes, right? Okay, so I'll start with a bad joke first. They're all terrible. Why couldn't Cinderella play soccer? Because she was always running away from the ball. All right, what did one eye say to the other eye? Just between the two of us, something smells. Neither one's good, but they're kind of cute, right? Okay, so today we are not doing iClicker, but you do have to sign in for attendance on the Excel spreadsheet. So please, please, please make sure your name is on the Excel spreadsheet for attendance today. Usually, even though it is the day after it is an exam, I do run clicker questions, because what should you have done before you walked in the door today? Watch which lectures? 3.1, 3.2, 3.3, right? And 3.4? Okay. We'll probably only get through 3.3 today, but we shall see. So it's really important that you watch those lectures before you come to class. Otherwise, you're going to be a little bit lost because you didn't get all the content. Y'all know I kind of review a little bit as we're doing problems, but it's not the same as lecture. And most of the time, if you struggle, the reason that you struggle is you don't watch the lectures before you come. So I know that's hard right now. I do realize that, but do your very best to watch them before you come. I feel like I was going to say something else about that. So iClicker is going to start again next Tuesday, and we'll have questions every day. So if we had iClicker questions today, what kind of questions would I be asking? From the lecture videos that you were supposed to watch. Okay, so I know that it's a struggle right now, so I'm trying to give a little bit of a grace period, you know, with a few things. But and remember that those iClicker points, a 70% is an A. So what is normally a C becomes an A, because and don't expect you to get it right away all the time. So 70% is an A, okay? All right, so I posted your exam grades on Moodle, right? We're having some issues with Pearson right now. So eventually you'll be able to access things on the Pearson site, but for right now, I at least wanted you to have your grades on Moodle. Okay, so you at least have those. And y'all did really well. Y'all did really well on the exam. So I was really pretty happy with y'all scores. Okay, and that's all on my list. Good. So today you really, 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 really need your best friend. Everybody got their best friend? And please make sure those masks are covering noses. Okay. All right, so this is my reminder that you need your periodic table today. Today is really a very important class because you're going to learn a lot of things that you're going to use for the rest of the semester. So if you struggle with this material today, I want you to get help either from me or from the tutoring center. But if you struggle today, you need to get help now, okay? All right, so what's the name of this chapter? Compounds and how elements combine, right? We haven't looked at combining more than one element up until now. So that's really, really what we're going to focus on. And if you look at the first section is electron arrangements and the octet rule. Why do we care about electron arrangements? Like, what does that have to do with anything? Yes, sir. So all elements want a certain thing. They all want to be stable. And what makes an element chemically stable or unstable? It is all about electrons. There are certain electron arrangements that are stable, and there are certain electron arrangements that are unstable. So if you look on the periodic table, which elements have really stable electron arrangements? Noble gases. Stable. When we say stable, let's see. When we say stable, stable means unreactive. So all those noble gases are really, really non-reactive. They don't want to do anything. They want to just hang out on their own. They're happy how they are. But the rest of the periodic table, they're not. They're to some degree unstable and are going to undergo chemical reactions in order to basically look like the noble gases. So I like to call the noble gases the cool kids, right? Everybody wants to be like cool kids. And why do they want to be like the cool kids? Because they want that same electron arrangement. Okay, so chemically, stable and unstable, reactive and non-reactive. So unstable means reactive, right? Okay, so all of this has to do with electron arrangements. But if you look at any given atom, every atom has lots of electrons, right? Can you rearrange all of the electrons in atoms? Or are you only going to rearrange some of them? Only some of them. Which ones? The outer electrons of the outer electrons. What do we call those outer electrons? Valence electrons. Okay, so these valence electrons are in the outermost energy level. So that's really the ones that are going to participate, will participate in chemical reactions. That's the abbreviation for reactions, RXN, reactions, chemical reactions. Okay, so if we want to be able to rearrange our outermost electrons, There are really only two ways that you could do it. What are those two general ways? Like, let's say I don't have enough electrons. I'm unstable because I don't have enough. What could happen to me? What could I do? I could gain some electrons, right? And the opposite of that is if I'm gaining electrons, then another atom must do what? Lose electrons. So that's one way. This is one way that we can change our electron arrangements, our electron configurations. What's another thing that could happen? I could share electrons, right? I could be really nice about it. And instead of giving and taking, I can share electrons. What do we call a compound that's formed because electrons have either been gained or lost? Ionic compounds. You ever wonder why do we call it ionic compounds? An ion is a charged atom. How do you get a charged atom? By gaining or losing electrons. So that's why we call it an ionic compound or an ionic bond, because that's what's happening, right? Okay, so what do we call the other kind of compound where we share electrons? So what is the co? Co means, like, you know, if you're co-captains, you're sharing being captain. So this is co, we're sharing what? What kind of electrons? Valence electrons. That's why we call it covalent, right? So the name is really describing what's happening with the electrons. So this is what we're trying to get to. And in order to get to this, we have to understand the electron configuration in neutral atoms and understand, okay, why are they going to do the things that they're going to do? Why are they going to lose? Why are they going to gain? Why are they going to share? All that kind of stuff. Okay. And so that's what we're going to focus on today, is why they're going to gain, lose, or share. Okay. So I really should have not taken up so much space. That's okay. I'm just going to erase. Okay. So when we look at the energy levels, let's see. Okay. Energy levels are basically how far electrons are from the nucleus of the atom. So you ever been to a concert, right? There are different kind of seats that you can buy for a concert, right? You could be in the mosh pit in the very front, right? Or you could be in the seating right beyond the mosh pit. That's my preferred, right? Okay. Then you can keep going back farther and farther and farther away, right? Well, the same thing is true about energy levels. That first energy level is like the mosh pit, okay? They're very close to the nucleus. And then as you get farther and farther away, you get higher and higher principal energy levels. And the farther an electron is from the nucleus, the more energy it contains, okay? So how do we know, just by looking at the periodic table, where are my valence electrons? What principal energy level are my valence electrons in? How far away from the nucleus are they? What we do is we look at the period. So for example, look at K, potassium. What period is potassium in? 4. So what is going to be my outermost energy level? 4. It's that simple. It's that easy. So if we look at potassium, look in 3.2, the very last one, D. D is potassium. How many elements, how many electrons are in potassium? 19. How did you get that number? How did you get 19? Because in a neutral atom, the number of protons is equal to number of electrons, right? So that atomic number on the periodic table is the same thing as the number of electrons in a neutral atom. So y'all told me in potassium, we have 19 total electrons. So my question to you is, how many electrons are in each energy level? How do you know what the maximum number of electrons could be in an energy level? There's a formula for that. What's the formula for that? 2n squared. 2n squared is our formula. So in my first principal energy level, I would do 2 times 1 squared, right? 2 times 1 squared is 1, 2 times 1 is 2, right? So in that first principal energy level, the maximum number of electrons that I can pack into there are 2. Okay, let's go to the second energy level. Now, actually, I want to show you something before we do that. Look on the periodic table. Look at principal energy level 1. How many elements are in period 1? 2. How many electrons can fit in the first principal energy level? 2. Okay, look at period 2. How many electrons fit in principal energy level 2? 8. How many electrons are in the second period? How many electrons? How many atoms are in the second period? 8. Oh, isn't this magical? Like, oh my God, the periodic table was arranged in a particular way. It's so cool. All right, so principal energy level 3. How many? There's actually 18. There's actually 18. But one of the orbitals in that principal energy level is actually weirdly lower in energy than the next principal energy level. And so do you see that? You see those transition metals? Basically, those transition metals are dropped down that way because their principal energy level of those valence electrons, the energy level's off. So count across in period 3. How many elements are in period 3? 8. So we're going to put, of those 19 electrons, we're going to keep putting them into the principal energy levels according to the periodic table because it's arranged by energy. That's how the periodic table is arranged, by electron energies. It's insanely awesome. How many electrons do I have left? 1. So where does that 1 go? What period is potassium in? So I have 1 valence electron in the 4th principal energy level. Isn't that cool? So my group, what group is potassium in? 1. So my period tells me the highest principal energy level of my valence electrons. What does the group tell me? The number of valence electrons. So 1 valence electron, this is told by our group. And the principal energy level of those valence electrons is determined by our period. Isn't that amazing?
So like when we do these, you don't want us to use the formula for the third energy level?
They can fit in that energy level, but that's not where they go because there are orbitals within the principal energy level where there are different energies.
So like when we do these problems, go by the periodic table instead?
Yep. Okay, go back 1, argon. See where potassium is on the periodic table? See, it's in 4th period, 1st column. It has 19 electrons. Drop 1 electron away. What element do I have? Argon. Argon is a noble gas. So what is it going to have? A stable outer energy shell, and we call that an octet, right? So argon has 18. So 2 of them are going to go in the first principal energy level. How many are going to go in the second? 8. How many are going to go in the third? 8. How many in the fourth? None. We're out of electrons. So look at this. This 8 tells me I have 8 valence electrons in the 3rd principal energy level. Having that complete octet is what makes those noble gases stable. Okay, so let's try the next one. F is fluorine. How many electrons in fluorine? 9. So 2 go into the first. How many go into the second? Only 7. So how many valence electrons do I have? What principal energy level are they in the second principal energy level. Isn't this cool? Okay, hydrogen. How many? 1. How many in the first energy level? 1. You always got to go low energy first. So here we have 1 valence electron. So if you look at the difference between hydrogen and helium, it's only 1 electron, right? Is hydrogen stable? You know, it is extremely explosive, very reactive, right? How about helium? Super stable, right? We put those in balloons for kids and say, have at it, right? You wouldn't do that if it wasn't stable. So how is it that helium can be stable when it doesn't have 8 electrons? I thought there wasn't the octet rule, right? If I could spell octet rule. You want 8 valence electrons in outermost energy shell, outermost energy level. Helium doesn't fit this rule. How many does it have? 2. How many valence electrons does it have? 2. Why is it stable? Because it has the maximum number. So if we do helium, total number of electrons is 2. In that first energy level, we're going to put 2. Do you notice how it's full? If I added 1 more electron, I would be lithium. And that next electron would go in the second principal energy level. So it has a complete outer shell. It has a complete principal energy level, but it doesn't have 8. So hydrogen is kind of weird like that. Yes, ma'am.
Okay, so back to what you had said about the how like you say how for like the third one you only put 8
Yeah.
instead of not being 18.
Yep.
So the fourth one would be 18.
The fourth one, you're going to put 2 into the fourth. Then you start backfilling into the third again. But you don't have to know all that. You don't have to know all that. Like, we're not going into that much depth. If you understand the periodic table and how the periodic table tells you about electron configurations, you're fine. So yes, if you are asked on the exam, how many total electrons can fit in the third principal energy level, what should your answer be? In the third, do your formula, 2n squared, right? So that's 2 times 3 squared. What's 3 squared? 9. 9 times 2 is 18. Technically, 18 can fit in that third principal energy level. But the weird thing is that they'll first go into the fourth principal energy level, then they'll come back to the third, and then they'll go back to the fourth. But you don't need to know all that.
So like you won't ask us about an element that would like have to do that? Okay. Is
Nope.
they're all just lower numbers?
Yeah.
So that one was basically just to figure out how many goes
In the total principal energy level, but it doesn't tell you the order that they go in. The order that they go in is kind of weird, but you don't have to know that. You don't have to know that. Because I know some of y'all did that in high school chemistry, but you don't have to do it here because we have other things that we're going to get to. Okay. So now I can ask you for any element on the periodic table, how many valence electrons are in there? Because how do I figure out how many valence electrons are present? What do I go and look at? The group number. That's all I have to do. Super easy. So carbon. What group is carbon in? 4A, or what's the other way sometimes you see it? 14. So everything in 4A or group 14 has how many valence electrons, no matter what principal energy level they are in? 4 valence electrons. That's my VE, is valence electrons. Okay, aluminum, what group? 3A or 13? What are the B elements? We keep saying A's, but what are the B elements? There's transition metals and the intertransition metals. Okay. So how many valence electrons? 3. Okay, lithium. What group? Group 1 or 1A? How many valence electrons? Okay, fluorine. 7A or 17. How many valence electrons? 7. Okay. So what did we say it takes to be stable? We want an octet, or we want a filled outer energy level, right? Most of the time it's going to be an octet. Most of the time it's going to be 8 valence electrons. So are any of the elements we listed here stable? No, they're not stable. They're not stable. So if I want to know if something is stable or not, that's what I'm going to look for. I'm going to look for valence electrons. So the next question says, which of the following elements are stable as atoms, right? Everything can change and turn into an ion, but we want to know for these atoms. So beryllium, how many valence electrons are in beryllium? 2. Okay, how many are in argon? How many in fluorine? How many in xenon? Now I'm going to add another one. Helium, how many? Okay, which of the following are stable? Argon stable, xenon stable, and helium is stable. Most of the time you're going to see an 8, but not always. So these are super happy elements because they have either octets or they have complete principal energy levels filled with electrons. Now, everybody wants to be like these. These are the cool kids, right? All of these. What group are they in? 18 or 8A? 8A. So everybody wants to be like them. And when I say be like them, I mean their electrons. So what we're going to do for the rest of the time is we're going to talk about how atoms will gain and lose electrons to have electron configurations like the noble gases, like the cool kids. Okay. So what happens when you become an ion? What's the definition of an ion? You have a charge. So this is a charged atom. How do you become a charged atom? You gain or lose electrons. Okay. If you're a cation, what has happened to you? You lose an electron, and if you lose an electron, you become positively charged. Let's look at an example of that. Let's say I have sodium. Tell me about this neutral atom. How many protons do I have? I have 11 protons. How many electrons do I have? By definition, it's neutral. I have 11 electrons. Of those 11 electrons, how many are valence electrons? Only 1, because it's in group what? Group 1. Okay, now I want to form an ion. What am I going to do? I'm telling y'all, everybody wants to be like the cool kids, right? But all these elements, they're lazy. They're lazy. They are going to take the easiest path to get to be like the cool kids that they possibly can. So sodium could gain, it's got 1 valence electron. It could gain 7. And what would it look like? Argon, it would look like argon. That's a lot of work. But I just told you the elements are lazy. What's another way that sodium could look like a noble gas? If it loses 1, then what would it look like? Neon. Oh, path of least resistance. That's what these elements are all about, right? They're lazy. So to get to be the ion, we're going to lose our 1 valence electron. Now, tell me what that atom now looks like. It's sodium. So did my number of protons change? No, so I have 11 protons. Did my number of electrons change? Yes. How many electrons do I have now? Okay, so if you have 10 negative charges and 11 positive charges, how many charges do I have overall? A positive 1. So we put a plus sign right there by the sodium. Okay, so now I have a sodium ion. When I'm saying it by itself, if it's a cation, I say the element name, and then I say ion. If it's in a chemical compound like sodium chloride, all I do is write the element name. Okay, so that's for a cation. All right, now let's talk about an anion. I'm going to erase the blue. Are y'all okay with that? Because I kind of wrote that in the wrong place, but I don't have a whole lot of room. Okay, so what's the difference between a non-metal atom and its anion? Let's pick one. Let's pick chlorine. Cl minus. Ooh, Cl. We're going to pick chlorine. We're not going to do the charge yet. Jumping ahead of myself. If it's chlorine, how many protons? I have 17 protons. How many electrons? 17 electrons. What happens, how many valence electrons are that? Is that? It's only 7 valence electrons because those are the ones that are in the outer energy level. Now, what happens to this non-metal atom when it becomes an ion? Remember the path of least resistance. These atoms are lazy, but want to look like those cool kids, those noble gases. So my choices are to lose 7 or to gain 1. Gain 1. So we're going to gain 1 electron. Now what do I look like? I look like an ion. I'm still chlorine, so I still have 17 protons, but now how many electrons do I have? I've gained 1, so now I have 18 electrons. So I have 17 positive charges and I have 18 negative charges. What's my overall charge? -1. So I put a little negative sign. So what's the difference between a non-metal atom and its anion? To become the anion, we must gain electrons. And when we do that, we now have to call it an ion, but we don't say the chlorine ion. What do we say? Chloride. So if it's the anion, we take the element and we add IDE, so we get chloride. That's how I know the difference between chlorine and chloride. Okay, good so far? Okay. How are the names of a transition metal atom and its cation different? Now, here's a weird thing. There are elements inside those transition metals that can have multiple charges. What do I mean when I say transition metals? From group 3 to group 12 are transition metals. So there are some in there that can have multiple charges. So iron, for example, could be a 2+, right? Carry a charge of 2+. Iron can carry a charge of 4+. But if I just said the iron ion, how do I know which one is which? I don't, right? So I have to name these differently. So I would call this top one the iron 2 ion. And then if I paired it with a non-metal, I would say iron 2 chloride or whatever it is, right? So this next one, Fe4+, I would call this iron Y'all know y'all Roman numerals? So what's 4? IV, because V is 5. And if you put the I before the V, it's subtraction. So this is iron 4 ion. How would you do a 6 in Roman numerals? VI, right? 4 is IV, 6 is VI. So if it's before, it's subtract. If it's after, it's add. Okay, all right. So how are the names? So we would have called the transition metal atom. We would just say the atom is iron. So you just do the element name. Whereas here, if we're going to do the ion has the charge. Oops. So the charge in Roman numerals in parentheses. If you're only talking about just the ion, if you talk about it in a compound, I would say iron 2 chloride. I wouldn't say the ion. But if you're naming just the ion, you say ion. Yeah, I know, complicated. Okay. Provide the charge when an ion is formed from each of the following. Before we do this, I want you to take out your best friend. Got your best friend ready? Okay, we're going to do this, but I actually don't want you to write this on your best friend. Because when you get to the exam, what is your best friend going to look like? It's going to be this with none of your writing on it. That's what I call blank. Okay, it's going to look just like this. So if I pick any element in group 1, group 1A, what's that charge going to be if it forms an ion? If it's group 1, how many valence electrons does it have? 1 valence electron. Is it easier to lose 1 or to gain 7? Lose 1. So what's our charge going to be? A charge of +1. Y'all see that? So every single thing in group 1 in the alkali metals is going to be a charge of +1. Everything, always, for ionic compounds. Group 2, what's my charge going to be? Okay, the transition elements, they vary, but we're going to say are positive. Right? You have to look at those Roman numerals. You can't figure that out without a little bit more information. Now, how about group 3A? How many valence electrons? 3. Is it easier to lose 3 or to gain 5? We're going to lose 3. If we lose 3, what's our charge? +3. Isn't this cool? Okay, group 4 can go either way. And so actually they tend to end up being more covalent compounds than ionic. So we're not even going to put anything there. Group 5A, I have 5 valence electrons. Easier to gain 3 or lose 5? Gain 3. So if I gain 3 negatively charged electrons, what charge am I? -3. How about group 6A? What's my charge? Group 7A? Group 8A? It's happy, right? They're happy. They're the cool kids. They don't want to change. They're not going to do anything. Okay. You should know that trend, but I would not write it because you're not going to have that on the exam. You can write it if you want, but you know what I mean? You're just not going to have it. Okay. Where was I? Did we finish this page? Oh, no. Okay. Provide the charge when an ion is formed from each of the following. Sodium. What group is sodium in? Is in 1A. So what's the charge? +1. Phosphorus. What group? 5A or 15. What's the charge? -3. Magnesium, what group? 2A, what's the charge? plus 2. Fluorine, 7A, what's the charge? -1. So what you're going to see is that metals, basically on the left-hand side of the periodic table, form cations. They're positive. Non-metals form what? Anions, which are negative. So if you're doing it and you're like, okay, there's chlorine, chlorine's a non-metal, it's going to have a charge of +1. You should go like, well, no, that's not right. Right? So it should be a good red flag for you. Okay. Next page. What page are we on here? Okay. How many protons and electrons are present in the following ions? Let me draw a little grid here. Those are going to be our protons. These are going to be our electrons. Extend that out. Okay. We're going to check our work. All right, aluminum has how many? Go find aluminum. What's the atomic number of aluminum? 13. So I have 13 protons. In a neutral atom, how many electrons would I have? I would have 13, but I'm not, am I neutral? No. So something's going to change. Look at aluminum on the periodic table. What is going to happen to aluminum? It has how many valence electrons? 3 valence electrons. So is it going to lose 3 or gain 5? Lose 3. So of my electrons, lose means subtract. I'm going to lose 3. What am I left with? 10. Now I'm going to check my work. I have a positive 13. I have a negative 10. What's my charge? +3 or 3+. And I go and check. Is that the same thing? Yes, I'm good. Isn't that kind of a nice little thing to be able to do? All right, let's do bromine. How many protons? How many total protons? 35. How many electrons? Do the same thing, 35. Now, it's in group 17, 7A, so it has how many valence electrons? 7. Is it going to lose 7 or gain 1? It's going to gain 1. So I have a total of how many electrons? 36. So let's check my work. I have a positive 35 because the protons are positively charged. The electrons are negatively charged, and I get a charge of -1. And that is indeed what I have here. Okay. All right, mercury, Hg. How many protons? 80. How many electrons? 80, but I have a charge of +1. Now, I'm a transition metal, right? Mercury. So I don't really know what's going to happen with it. So I have to actually look at the charge on the mercury to determine how many electrons I have. So if I have a charge of +1, that must mean that I have 80 positive charges, right? And then to have an overall charge equal to +1, what has to be in there? I have to have 1 less, right? So -79. Right? So how do I get 79 electrons? I take away 1. So mercury will give up 1 electron in this case. It could do other things, but in this case. Okay, nitrogen. How many protons? 7. How many electrons? 7. Now I'm in group 15. Am I going to lose 5 or gain 3? I'm going to gain 3 electrons to get a total of 10 electrons. So I have a +7, I have a -10 for a total of what charge? -3, and they check out. Mhm. Correct.
So let's say it was 8 and it was mercury, but with a 3+.
So sure. So Hg, it would be 3+. If it's mercury, it's got 80 protons, right? Okay, so we know we're going to start with 80 electrons, but something's going to happen, right? So I know that I have a +80, and then I have a negative some amount of electrons, and that has to equal to +3. So I have to have 3 more protons than I do electrons. So how many? 77. So that would be -3 gives me 77. Okay, good. All right. Now we have to name them. Now, because we're naming these ions, remind me of my rules. If it's a cation, what do? I just do the element name. And if I'm just naming the ion, I say ion, right? What if it's an anion? You do the beginning of the element and you end it in IDE. Okay, so how many anions do I have in this list? 2 anions. See how they're negatively charged? Let's do those first. Br is what? Bromine, but we're not going to call it bromine. We're going to call it bromide. And in the homework, no capital letters. Don't mark it wrong. No capital letters. Okay. Okay. N3-. It's nitrogen, but instead of being nitrogen, it's nitride. Okay. Now let's do our cations. Al3+. Aluminum ion. Hg+. Ah, I heard somebody say it. 1. Why did you put the 1 in? It's a transition metal. It's a transition metal, so we have to put it in. Now, I'm going to do one. What do I call this one? Now, normally we would have to put a Roman numeral, but I'm going to tell you that there are 2 exceptions to that rule. Let me show you on the periodic table. If you see these 3, aluminum, zinc, and silver, what's the charge on aluminum? It's not a transition metal, so it's always going to have the same charge. What charge is it? +3. There are 2 transition metals that are unique that will only have 1 charge, and you therefore never have to write a Roman numeral. Zn is always going to be +2. Silver is always going to be +1. Do you see the trend? 3, 2, 1. That's how you remember it. Okay. So these 2 transition metals will always be the same, and so you don't write Roman numerals. Don't put Roman numerals for Zn and Ag. Okay? And you will need to know those. Okay, so we just leave that as the silver ion. Okay. Name the following ions. Oh, my goodness. Okay. What's that first one? What's A? Copper what? Copper 2 ion. Now, if we had this in a compound that was copper and chlorine, I would call that copper 2 chloride, right? I wouldn't say the ion part. I only say the ion if I'm just naming the individual ion. Okay, SO4 2 minus. So this is sulfur and oxygen. It's more than one atom from the periodic table. So if you look at both B and C are called polyatomic ions. What does poly mean? Multiple. What does atomic mean? Atoms. What does ion mean? Charged. So this is multiple atoms combined together that have a charge. Hey, they named something really well for once. All right, so do you have to memorize all of your polyatomic ions? No, I'm not that mean. Who should you go and see? Your best friend. Your best friend grows with you. Okay, you have polyatomic ions. Yay! Not everybody gives you these. You should be happy. So go and find SO4 2 minus. What is it? Sulfate ion, right? It's the sulfate ion. And you wouldn't put ion if it was in a compound. Okay. HPO4 2 minus. Hydrogen. What? Phosphate. Hydrogen phosphate. What about, let's do D, let's do P 3 minus. What do I call that? Phosphide. So the end is super important. If I say phosphate, that's PO4 3 minus. I got this DE. I got this from the polyatomic ion table. I got phos, PHOSPH8, phosphate, right? So the ending is super important. Be very, very careful about that when you're reading these. Okay. All right, now we've done just one atom. Now we need to talk about multiple different elements coming together and giving and taking electrons. All right, so if I'm a cation, what have I done? I'm a cation. What's the definition of a cation? It's a positive ion, so it has I love cats, so cats are positive for me. That's how I remember cation and anion. Cats are positive. I like cats. Okay, so how do I become positive? I lose electrons, but I didn't just lose it out into the ether, right? That electron that I lost, call it lost, it's not really lost. Somebody picked it up. Who picked it up? Another atom picked it up and became a anion because that has gained electrons. And ions are negative because they have no cats. All right, so when you think about ionic compounds, I want you to be thinking about who's giving however many electrons to somebody else, right? It's not just that you lose it and it goes away. That electron goes to another atom. And it's really important to keep track of how many are being given up and how many are being taken. And so that's what we're going to talk about. Okay, so let's look at 3.22a. We have to give the formula and name for the ionic compounds formed from the following pairs of electrons. Okay, potassium. If it's not a noble gas, it's unhappy, right? And it's going to take the path of least resistance to go and look like those noble gases. So what is potassium going to do? So potassium's in group 1, it has 1 valence electron. Is it going to gain 7 or is it going to lose 1? Lose 1. So what charge is it going to be? +1, or we just put a plus? Okay, chloride. What's up with chlorine? How many valence electrons does chlorine have? 7. So is it going to lose 7 or is it going to gain 1? Gain 1 to become negative. So that positive and negative, we understand that those are ones, right? Okay, so if potassium gives up the electron, gives up 1 electron, what is chlorine doing? It's gaining 1 electron. So I could say that potassium is giving 1 electron to chlorine. So how many, what's my ratio of chlorine atoms to potassium atoms? 1 to 1, right? For every 1 potassium, I have 1 chlorine. So when I write a chemical formula, that's what I'm writing. So if I want to write the chemical formula for potassium and chloride together, because it's a 1-to-1 relationship, I write KCl, right? It's a 1-to-1. Okay. And I need to name it. How do I name that? Element name for the cation is potassium. And then chlorine is really, because it's an ion, chloride. Okay, I'm going to teach you a trick. You can do this where you find the charges and you say, okay, this one's giving how many electrons, this one's picking up how many electrons, that's my ratio. Or you could do it the easy way. The easy way is the crossover. I know K is a +1, I know Cl is a -1, so I'm going to go ahead and put those ones just for fun. Okay. The charge on the cation, if you take that and turn that into the subscript, so you drop the charge and you just keep the number. And then you do the same thing and go the opposite direction. And I take the charge that's on the chlorine and I make it the subscript, but I drop the charge and I put my 1. Now I have my formula. So if I want to write my formula, I don't include charges, so I don't include the things that I've circled. I only include the things down here. So that would be K1, Cl1, but do we write the ones? No, we really just write KCl. Now that shortcut is going to work for everything. And it's super nice and it's super quick because you're going to have to be able to do these pretty quickly. All right, so let's try another one. Zinc and oxide. So tell me about zinc first. We do a different color. Zinc is a, Zn is a +2. Oxide is a what? 2-. Okay, so tell me about this Zn2+. Zn2+ is going to give up what? 2 electrons. Where are those 2 electrons going to go? Oxygen. This 1 oxygen atom is going to gain 2 electrons. So this 1 zinc atom gives 2 electrons to this 1 oxygen atom. So what's my ratio of zinc atoms to oxygen atoms? I have 1 zinc atom giving up 2 electrons to 1 oxygen atom. What's my ratio of zinc to oxygen? 1 to 1. So I write that as ZnO. Let's check to see if my crossover will work with that. Okay, so I'm going to erase what's underneath here. Okay. I'm going to take my charge on my cation and turn it into my subscript. I'm going to take my charge on my anion, turn it into hello. Don't do that. It's a 2. Okay. And cross them over. Y'all see what I did? Yeah. Okay. So now I want to rewrite it. Zn2O2. That's telling me for every 2 zinc atoms, I have 2 oxygen atoms. Can I reduce that to what? 1 to 1. So I really have Zn1O1. Does the crossover work? Absolutely. Absolutely. It always works. It always works. Okay. C, copper 1 and sulfide. Copper 1. How do I write that? Cu and a plus. Sulfide is what? Sulfur, but it has a charge of -2. Okay, now let's think about this logically before we do the crossover. I have 1 copper atom. How many electrons can it give up? Only 1. If sulfur picks up 1 electron, is it happy? It's not. It's not enough. Sulfur says, I need some more copper. So I get a second copper atom, and that second copper atom donates 1 electron to that same sulfur atom. So how many copper for how many sulfur? 2. So I need 2 coppers for every 1 sulfur. That's Cu2S. Let's check and see if our crossover works. I'm going to erase my zinc stuff. So I got rook. Okay. So if I have Cu, it's a plus, and S, that's a -2. Okay, so let me do the crossover. I'm going to take the charge here. And I don't know what this is. I didn't erase very well. Okay. So that +1 just becomes a 1. This -2 becomes a 2. What do I get? Cu2S1, but I don't write the 1. Did I get the same thing? Yes. So it works. All right, but I think in this one it said we had to give formula and name. So we got to go back and name things. So Cu2S, what do we call that? Be careful. Copper 1. Copper 1. I got to erase some of this. I didn't give us enough room, did I? Copper 1. Sulfide. Okay, how about ZnO? Zinc oxide is correct. Why isn't it zinc with a Roman numeral? Because we know from the periodic table going down, zinc is always going to be +2. Okay. All right. So now we have to give the number and type of each ion present in each of the ionic compounds that we did up here, right? So I'm going to write the formula for each one. We had KCl, we had ZnO, and we had Cu2S, right? I just copied our answers from before. Y'all with me? Yes? Okay. So for potassium chloride, I had K, what was my charge? Plus, right? So that's the potassium ion. How many ions do I have? 1, right? How did I know that? The subscript here is understood as 1. So how many chloride ions? There's nothing there, so that must be 1. So this is 1 ion, 1 chloride ion. Zn, what was my charge on Zn? +2. So how many ions do I have as Zn? 1 ion. How many of oxide? What's the charge on oxide? -2. How many? 1, because it's understood. Okay, and obviously I did not leave enough room for this. Okay, Cu is a what? Plus what? +1, because right here I see it's a 1, so it's a +1. So my copper ion, how many? Ah, that subscript tells me 2. I have 2 ions. Now the S is a 2 minus, right? But you only have how many ions? 1 ion. Okay. All right. So now what we want to do is we want to give the formula and the name for the ionic compound formed from the combination of this metal and acetate. So what is acetate? It's an example of a polyatomic ion. It's a polyatomic ion. Okay, so let's do them here. So what kind of a ion does sodium form? Look on the periodic table. +1. Now, acetate all together, C2H3O2. This whole thing carries a charge of -1. All together. You cannot break this apart. You cannot change anything in here. So do your same crossover method. The charge on one becomes the subscript of the other, and vice versa, right? Now, if you have a polyatomic ion and you have a subscript that is greater than 1, you must put the polyatomic ion in parentheses. But if it's just 1, you don't have to put it because it's understood, right? So I wouldn't write Na1 C2H3O2 in parentheses 1. Right, because all those ones are understood. So I would just write it as NaC2H3O2. Make sense? But if this number is greater than 1, you have to have the parentheses. Okay, so let's do B. Iron what? 2 plus or minus? 2 plus, okay, and then acetate is C2H3O2 minus, and that's a 1, right? So I'm going to do my crossover. So I rewrite it. What do I get? Fe, and there's a 1, but I'm not going to write that. I'm going to write C2H3O2, close parentheses, and then put the 2. What happens if I left off the parentheses? What would it look like? It would look like I would have 22 oxygens. Do I have 22 oxygens? No, I absolutely do not. So that's why you got to be careful about those parentheses. Okay. Oh, and we need C. Oh, and what are we naming them? What are we doing? Formula and name. We have to name them. So what do we name this one? This is sodium. And we don't have to say ion because it's in a compound, sodium, and then you just name the polyatomic ion. Sodium acetate. How do we name B? Iron what? Iron 2 acetate. Iron 2 acetate. Don't forget that 2, because if it's a transition metal and it's not zinc and it's not silver, write your Roman numerals. Okay. All right, so now C. C was aluminum. What's my charge on aluminum? +3. And then my acetate is C2H3O2, and it's just a -1. So do your crossover. What do you get? Al. And then before you do the C, open parentheses, C2H3O2, And then we're going to close parentheses and put the 3. So how do we name this? Remember, no capitals. Okay, pretty good. You got this. You got this. All right. Okay. Oh, and give the number and type. So I'm going to do 3.28. I'm going to go back and do it on the other page. But for everything that we did, we need to give the number and each type of ion present. Let me go back. Okay, so for sodium acetate, let's do it in black. Let's do a thin one. So for our sodium ion, Na+, how many do we have? 1 ion. So for acetate, C2H3O2-, how many do we have? 1, because technically it's this whole thing in parentheses with a subscript of 1. So that's 1 ion. Okay, iron 2 acetate, how many? This is where it gets tricky. If I say iron 2 acetate, how many ions of iron do I have? You still have 1. Because the 2, does the 2 refer to how many you have here? No, what does it refer to? The charge. I'm telling you, so many people get tripped up right there. So be careful with that. Okay, and then the acetate minus, we have 2 ions. See the difference? Okay, so aluminum acetate. How many for aluminum? Our Al is a 3+. We have how many? 1. For our acetate, I have 3 ions. Okay. Ready to move on? All right, here we go. Oh yeah. And that is the end of section 3. And so I ended last class at 3.3. So we're going to end today at 3.3. Now, before you leave, this section, these sections were super important because we are going to use them for the rest of the semester. So if you are struggling with this material, you need to get help now. Come and see me, go to tutoring, come talk to me, let me help you, but don't get behind on this. Understood? Okay, y'all have a great weekend. Clicker questions on Tuesday. All right, anybody on Zoom need anything? Y'all need anything on Zoom? Because if you don't need anything, you are free to go. Good, awesome, great. All right, I'm gonna go ahead and end the Zoom.